This PowerPoint is over conservation of energy. Now, types of energies can be categorized into two different types. You got conservative energies, which is sometimes called mechanical energy. These are types of energies that you can increase or decrease these amounts. And then you have non-conservative energies. Non-conservative energies usually are contributed to like outside work that's being done on the system. So those are energies that either they constantly increase or they constantly decrease. We'll get to those in a second. So the types of conservative energies that can increase or decrease are referred to as kinetic energy, gravitational potential energy, spring potential energy, or rotational energy. Now, these types of energies, you can, kinetic energy deals with how fast you're going. So if you increase your speed or decrease your speed, you can increase or decrease kinetic energy. Spring potential energy, for example, is when you stretch a spring. By stretching the spring, you increase your spring potential energy, and then you release it when you let go of it. And then rotational energy, when objects are rotating, they can increase or slow down and decrease the rotational energy. So those are all the conservative types of energies, because those types of energies can either increase or decrease. Now, non-conservative energies are type of energies that only go in one direction. For example, an applied force. So if somebody is pushing on a force or pushing on an object, that's applying a force, and then that force does work. It does actually what's referred to as positive work. So it puts energy into the system, but it only goes in one direction. That applied force can't take energy really out of the system. So an example of like thrust or chemical energy, these are types of energies that if you think of combustion is a great example of chemical energy. Once that energy is released from gasoline that's burned, then that energy is gone and you can't get it back. So it always does positive work, and you lose that energy to chemical. Now, friction is another type of energy, usually called dissipated, and it's caused by heat and sound. This is your negative types of energy, so you lose this type of energy in your system. Friction takes energy out because it does work on your system to slow it down, so it takes that energy away. But friction doesn't really add energy back to the system, so it only goes in one direction. So these are effectively your two types of energy, your positive work and your negative work that's done by outside forces that do non-conservative energy. Now, in conservation of energy, the definition of conservation of energy says that in a closed system, energy will transfer from one type to another, but the total amount of energy will not, the total energy will not increase or decrease. So you don't lose any energy, you don't gain any energy as long as it's a closed system. Now, the purpose of a closed system is to say that there's no outside net force. There's no work being done on the system or by the system, that all the energy that's inside the system is going to stay inside the system, but it just transfers from one type to another. So if you can kind of think of this as buckets of water. So I got my example here. I've got gravitational potential energy and kinetic energy. So if I pour water out of the bucket into another, then that's transferring energy from one type to another, but we don't lose any of that energy. So while the energy transfers, the energy is going to be conserved even though it's in different types. Now, the next one, if we spill water, then that's referred to as negative work. We lose energy out of the system. So just like spilling the water out, that's negative work being done. It's dissipated energy. Things like friction, heat, and sound, those will do negative work on our system. The next thing is adding water. If we add water to our system, that's like doing positive work. So we add more energy into the system. So negative work is spilling that water out. Adding energy, adding water is doing positive work on our system, increasing the amount of energy that's in our system. All right, so in this example, we look at what happens. This is called an energy diagram. We look at what happens with the energy as it transfers from one type to another. So we start with gravitational potential energy. This dashed line refers to how much energy we start with at the top. And then as it comes down, it's going to lose that gravitational potential energy because it loses height. But in the process, it speeds up, and that's where we get kinetic energy. The kinetic energy is going to increase because we're getting faster. The gravitational potential energy decreases because we're losing our height. And then as this transfers, we get more speed, but we lose height, so we get more energy to transfer. Now you'll notice the amount of gravitational potential energy we started with is equal to the amount of kinetic energy that we gained in the process. And as it moves at a constant speed along a level surface, then we don't have any more energy that is transferred. Notice there's no dissipated energy because we don't have any air friction in the process. So to look at the entire process from beginning to end, it would look like this. So energy transfers from one type to another, and in that process, we don't lose any energy. The total amount of energy stays the same. In this process, we're going to add air friction in here. So that means we're going to include some dissipated energy. That means as the gravitational potential energy decreases because we're decreasing our height, then we have kinetic energy that is increasing. And the reason kinetic energy increasing again is because we're getting faster. But we're also increasing the dissipated energy because we have friction that takes energy out of the system. Now the purpose of this is to show that the amount of kinetic energy added to the amount of gravitational potential energy wouldn't be equal to the initial because we have some dissipated energy. So all of these added together give us our total amount of energy. I have energy that transfers from one type to another, but the total amount I start with is equal to the total amount I end with. So as it goes down, we lose gravitational potential energy, but that goes over to kinetic and dissipated energy. Now at the bottom here, it's going to slow down because we have friction, so that means we lose kinetic and goes over to dissipated. Now the entire system, if we go from beginning to the end, it would look like this. So you can see in the process, we're going to transfer energy from one type to another, but the total amount is going to stay the same in the process, just from one type to another. In this one, we have a book that's falling. We don't have air friction, so as it falls, the gravitational potential energy converts over to kinetic. And then we get down to the bottom where all the gravitational potential energy is going to be kinetic, but once it hits the ground, it hits the ground and stops. So all of that energy is now going over to dissipated. Now, how do I know that? Well, I have no more height and I have no more speed, so therefore all of it has to be over and dissipated. Now, the entire system looks like this when it goes through. All right, so again, we start with gravitational potential, converts over to kinetic until it hits the ground, and then we lose all of it. And the reason we know we lose that dissipated energy is because we hear it. The sound is part of dissipated energy. All right, so now we have an object that starts from a height, and this is a bouncy object, and there is air friction. So as it falls, we have some gravitational potential energy that converts over to kinetic, but it also converts over to dissipated because we have some air friction. You'll notice this last little column here that we have U sub S. That's referring to spring potential energy. The spring potential energy because when that ball hits the ground, it'll bounce. So as it falls, we lose gravitational potential over to kinetic and dissipated all the way until we get to the ground. Once we get to the ground, now it's going to spring, so it's going to stop, meaning we lose that kinetic energy, and that energy goes over to spring potential, but it also goes over to dissipated. Now, as it springs together and stops, then we have some spring potential energy stored up, and then that spring potential energy we get back as it bounces back upward. But in the process, we're still losing energy over to dissipated. So that each of these lines show this is where the kinetic energy was when it started to bounce, and then this is where the kinetic energy is when it starts coming back up. Now, because we have dissipated energy, all the energy is not going to go back over to gravitational potential. We have kinetic that goes over to gravitational potential, but then we have some dissipated energy in the process. And this is why an object that bounces from a certain height can never get back up to that certain height, because we can never have that dissipated energy go back into any form. This is a non-conservative energy, and therefore once we lose energy to dissipated, it is gone and we can't get it back. So the gravitational potential energy can only be so high, and therefore the height can only be so much. We can't get back up to that original height because that original height will require more gravitational potential energy than we have. So the entire process would look like this. All right, so these energy diagrams, they show what happens to the energy as it transfers back and forth, but the main idea is that energy is conserved because the amount of energy I start with is equal to the amount of energy that I end with.